Okay, we're back with this clock generator. So in the last video we had a look at the SI5351A IC. Now we connected it up to this radio. We basically managed to get it controlling the frequencies on the radio, and we did a test and it actually works reasonably well. I mean, we were getting some good results from it. It was a lot cleaner, the signal we got from this than we actually got from the original phase lock loop. Now, there was a couple of issues. Now, one of those issues is that we're unable to modulate FM from the radio once we bypass the VCO and PLL circuitry, because we're not using the local oscillator in this. So today what I'm going to go through is this bad boy, which is the B version. It's the SI5351B, and I don't know if you can see that they're very small ICs, and I've got a little breakout board. Now it's for this form factor, of the package. And what is it? Let's have a look. It's a 20 QFN package. So what I'm going to have to do is make some circuitry around this. And if we actually look at the original, you probably think, well, why can't we just connect, remove this one and replace it with a B? Well, we can't, because it's the pinout's wrong, and the package shape is also not the same. So it just simply wouldn't work. But if we also look here, we've actually got some other components on here. And basically what all these are is we've got a 3-volt regulator here, and we've got a couple, I think they're just N-channel MOSFETs. And what they're doing is doing some voltage line conversion. Okay, you're probably asking yourself, so what's all the kerfuffle about the type B of this clock generator? Well, obviously this is the type A here, and you can see we've got 2 PLLs, and that would allow us to give us 2 independent clock waveforms, basically between, I think it was 8 kilohertz and 160 megs at any frequency on 2. And we could have a third, but it would have to share one of the PLLs. Now, we went through all this on the previous video, so I'm not going to cover its operation. But that's the type A. So let's have a look at the type B. Where are you? Yeah. Okay. Now this one has got a VCXO, which is a voltage controlled crystal oscillator. That's what it does. And you've got this thing here, it says VC, so we can actually vary the voltage here, and then theoretically we can adjust the output frequencies from here, from the device. Now, the main differences of this is pretty obvious. This has got 1, 2, 3, 4 pairs of outputs. So we've got a lot more outputs on there. We're not really interested in using them. Well, I'm not at this stage. But it's this VCXO that's the appealing part. Now, I do know they do make breakout boards for these. There are some made with loads of sockets on them. I've seen them. I haven't got one, I haven't tried one, so I can't really comment on them. But what I have managed to do is get this IC from DigiKey. Now, there's a couple of versions of it, but we can talk through that later, because they come pre-programmed from the factory, some of them, and some of them don't. Now, we'll cover that as we go on. So the plan is, because we don't have FM, I was hoping that if we put an audio signal on this VC point, we should be able to pull the main frequency enough to cause modulation, so we could start deviating the output signal at this point. Now, we know these are pretty rough when they come out of this thing, but if you put it through a bandpass filter, as we've discovered, it really cleans the signal up, so it's good. So I think, all things being equal, I reckon if we put an audio signal at this point, we are going to get an FM modulated signal at this point. And if we have a look at the schematic diagram of the 11 meter radio. Okay, so if you're new to the channel and you like this content, please consider subscribing or you know, hitting the like button, as it really helps the channel. We're trying to grow the channel, so you know, thank you in advance for your support. Okay, so this is the multi-mode 2 11 meter radio. This is the one we've been modifying, and you know, this has got 3 forms of modulation on it. Obviously, we've got single sideband, AM, and FM. Now, all 3 of those modes are modulated completely differently. So, what I mean by that is how they've done it. So, for single sideband, there's a section here. We've got the TXIF that comes through, and then we've got a balance modulator. And so, because a long story short, we will basically send, I think it's this one, the TXIF with a single sideband component up to this mixer. Then this mixer just mixes up the local with the local oscillator coming from this synth board, and then at the output of which we've got a bandpass filter to clean up all any unwanted spurs and harmonics and other order products, and then off it goes down into the RF power amplifier. So that's how in single sideband works. Now AM's again slightly different, because what we're doing is there's these 2 transistors here, which is the driver and the power output device basically. And what is happening, we've got this line here. Now that is coming up from the audio amplifier. So when we're in when we're in transmit mode on AM, the audio signal comes up here, and what it'll do, it will modulate the audio signal. It basically mixes it with what's coming out of this mixer, and that's that's producing amplitude modulation. That's the way they do it on these radios. There's other ways of doing it, obviously, but these type of radios, this is how they do it. Okay, and then finally we get round to FM. Now FM is a little similar, because again we're sending the mic audio path through the power amplifier. And you've got to remember, this is the power amplifier. Amplifies the receive signals that that we can hear coming out the speaker. This is the IC that's doing it. And if we've got this point here, point H, that connects up here somewhere. Yeah, it's there. So let's just zoom in a bit and have a look at this. So what's happening is the audio signals come up here when we're in FM mode. Now I'm not sure how this switches. We don't want it doing this when we're on AM or sideband. So, but it comes up here. You've got this pot here. I imagine that's for your deviation level. But ultimately, what it's doing is it's pulling the frequency being produced, which is the local oscillator frequency. It's actually pulling it and producing an FM modulated signal. So the FM is modulated on the local oscillator. Sideband is modulated on the TXIF, and AM is modulated by mixing the audio signal with the dead carrier in the RF output stage. And that's the way it works. So obviously we've bypassed all this. But in doing so, we've stopped, we can't modulate. So the idea is using the B chip. Hopefully this will get round that problem. Okay, now you can see I've got this thing together. Now, I had to use the hot air to get this QFN device on to this little breakout board. But I've made up the circuitry. I've made a little prototyping board. I know it doesn't look very impressive, but it's just prototyping, and I've been experimenting with it, and that's the basis to development work, I guess. But that being said, it's not too bad. So let's just go through it. So we know we've got our BIC here. Now this runs between 2.5 and 3.3 volts. So at the back here, I've got a 3.3 volt regulator, and over here, this is just a line conversion ready-made board. I bought you pick them up and say neither really cheap. But that's to convert the I2C down, and there's a little reference oscillator, 25 meg crystal there, which is a surface mount device, but I've managed to get it on the 0.1 gaps. There's 4 pads, 2 are ground and 2 are the actual crystal, and that connects up directly into the IC. So the connections we've got on here, this is 5 volts, which is coming from the Arduino, which is coming into the board here. We've got our I2C, again, coming from the Arduino, which comes into it here, our STL. And this is audio. Yes, audio. I've put some filter in. We'll go through the circuit in a second. And that's the RF out. So that's our clock gen out. And if we look here, I don't know if you can see, if I bring it into the picture, I'm just using a bandpass filter. I used it in the last video. It's a 14 meg filter designed for the 20 meter band, and that is simply to clean the waveform up. Okay, so I've got, this is coming from the clock generator, and I'm feeding it into the the low power input on this test set. You can see it's actually producing a signal, 13.99723. This is a bit out of calibration. I need to get a standard for in here, but yeah, one fine day. And we're getting 206 microwatts. That's what it's telling us, how much energy we're actually sending into the test set. So yeah, that's the clock generator. Obviously we're set to around 14 megs because I want to use this signal generator. Just on the scope there, we're looking at the waveform. And if we come over here, on this set, I've got this set up as an audio tone generator. So basically move that out of the way. So what we've got, goes into our audio, into our SI5351B in the voltage control section. And if we send 900 millivolts into it with a tone, obviously we're AC at 1 kilohertz. If we turn that on, you can actually hear it. So if we look back over here, okay, so for 900 millivolts, I can produce just shy of 2.6 kilohertz of deviation. Let's see if I can move that light so it's not so glaring. And to be honest, it's working quite well. If I can change the frequency down, so if I change the SIGGEN frequency to say 400 hertz, you see the waveform. Yeah, it's got it's got a little bit of deformity on the top. So if I bring the voltage down a touch, there we go. That's tidied it up. So that's at 809. So yeah, 2.25. So yeah, I mean, look, if you're going to modulate a radio, I think the deviation setting on those 11 meter radios is about 1.5 kilohertz anyway. So it's well within there. I'm quite confident that is good. If we start to increase it, the waveform, it starts to, you can see it. That's at 1.3 volts. You can see, you can actually hear it. It's starting to misshape. But yeah, what's that? We'll pull it back down. Is that about 900? Yeah, that's about 900. Yeah, so 900 we're getting, the waveform. It seems that it's more susceptible to the lower frequencies getting distorted at high levels. So if we change the frequency back to 1 kilohertz, yeah, I could actually wind that up a bit. So let's have a look what I can take that up to. Yeah, so I can get just shy of 4 kilohertz deviation out of it. you know, and that's for 1.37, yeah, so it's 1300 millivolts. But if I put that back on 400 hertz, that's the acid test. So if we go frequency, you can see it starts to distort. So yeah, the real sweet spot with this for the maximum is about 2. Yeah, no, it's not too bad there, is it? It's at 2.8. So yeah, so we could probably get about a good 2.8 kilohertz of deviation out of it. And for two-way radio, that's perfect because you don't need any more than that. It seems to work extremely well with high frequencies. In fact, you know, you could send data with this thing, and I would imagine it would work extremely well. So yeah, so that's for 977 millivolts. You know, 400 hertz or 0.4 of a kilohertz. But that's it. Yeah. It's going good. Now, the real test will be to put it on the radio. Now, the radio works at 39 megahertz. That's thereabouts. So, yeah, there's a bit to this. And if you were planning on doing it, at the end of the video, I'll go through some of the programming. Because a lot of people have tried this, and a lot of people have failed to get this working. And it's to do, a lot of it's to do with the coding. So let's have a look at the circuit diagram of what I've actually built in this board. Okay, so this is the schematic. I've done this in Eagle. I'm going to possibly design a board, but I want to put more in it. But for the moment, this is perfect. So well, let's just go through it. So I've got basically got a header here. This is at JP1. You can see I've got different headers. I've just done that for ease, so I can just note them. So basically we've got ground and 5 volts, which is coming from our Arduino, and I've got this voltage regulator here. It's, I think it's 100 milliamps, and it converts down to 3.3 volts. We've got a couple of capacitors here. That's to do with some decoupling, so I want to try and keep the noise out of this circuit and from coming out of this circuit. So yeah, it's just a little 10 microfarad, 10 nanofarad. And then on the output, yes, we've got our 3.3 volts. That's just supplying a rail. And I've got 100 nanofarad capacitor there, again decoupling, trying to suppress any noise. So then it breaks off, and we've got the star of the show, which is the SI5351B. Now you can also get these in a 16 QFN package with less outputs. Just a quick note, I couldn't get one, they weren't available when I was getting this. I picked this up from DigiKey. But yeah, the outputs we're not using, well, we've got these VDDOs. These are basically supplies to voltage controlled amplifiers, and they just control the the amplitude of the waveform coming out of the IC. So in the data sheets, if they're not being used, tie them all high. And I didn't do that when I was experimenting, and it was doing strange things. And as soon as I tied them all high, then it was working fine. So yeah, that's obviously important. We've literally just got a 25 meg crystal. I think it's about 10 ppm parts per million. This is a cheap one. It's 8 picofarads. Obviously, the datasheet talks about it wants the correct capacitance. There is some tolerance, and I think you can do it in the coding, but we can look at that later on. But that literally just connects to XA, XB, and that just makes up its local oscillator. And here we've got our SCL SDA, which of course is the I2C. And if I just zoom out and go through, well, they're coming through these two circuits here. And all this is some voltage conversion, because of course our Arduino, you know, it's a 5-volt device, and that goes for the it goes for the I2C as well, because what will happen is, you know, it'll be switching from, you know, low, which is obviously 0 or thereabouts, to 5 volts. And obviously with this device only being a 3.3 volt device rather, yeah, we need to convert it. And I've done it using, you know, this is a very standard way of doing it, using these N-type MOSFETs and some pull-up resistors. So this is the high side, 5 volts. This is the low side, and this is bi-directional, so you'll get bi-directional communication, you know, to and from the you know, the main clock oscillator device. So yeah, but that all works really well. So, and again, these are just the rails tied to the 5 volts and the 3.3 volts. So that's the conversion. Obviously over here, or we said we tied those, but that's the VD, that's the power, so that's the 3.3 volt rail. I've got a 4.7. I'm planning to use a little tantalum and a 10 nanofarad, which has got to be very close to this. Again, the data sheet talks about, you know, care, you know, you've got to take care of your decoupling to try and keep everything, you know, the noise out of everything. So the big idea is so it works properly. Okay, and then we've got this section, VC pin 3. Now I've got R1 and C6. Now I've calculated this because that makes up basically a it's an RC low pass filter, and if you calculate that, there's about a 3 dB drop off when it starts to roll off to get to the cliff. That will be around about 6 kilohertz or thereabouts, which I thought, yeah, it seems to be working okay. The real test is when we get it in the radio. I've got this capacitor here, 4.7. I've actually put 47 microfarads in there, so that's wrong. I'll have to correct that. But again, a lot of it's been trial and error. I've just been literally trying stuff in there and just reading what it says in the data sheet, you know, trying to go by, you know, what they recommend. But that literally comes up and goes up to the header, which I'm currently feeding with an audio generator. So, you know, at this point, the maximum you could really give it is about 900 millivolts, and 900 millivolts for 14 megs will be giving you, you know, about 2.5, 2.6 kilohertz of deviation. Yeah, it's pretty good. It's working well. And obviously, here, this is a clock output on pin 13 that goes out. I'm debating whether to put a little 0.01 capacitor in there, maybe not, because I've actually got one on the radio. So yeah, I will do that. On the board, I'm going to put I'll put a 10 nanofarad cap in there, and that should solve that issue. Yeah, but that's basically about it. There's not a lot there. Now, you know, the devil is in the detail, it's in the programming, but that's the circuit. I mean, I've just come up with it. I've just, from what I've read on the data sheet, then, and obviously I'm looking at the A version on the breakout board, and you know, if you look at them, there's not a lot there, is there? So, you know, that's how I've come up with it. So if I can, you know, work out how to get this onto a PDF, I'll leave a link in the description. And yeah, for the code as well. Okay, well, let's get this connected up to that 11 meter radio and see what we're getting. Okay, so I've got everything set up. You know, I'll bring that into the picture. It's the Arduino, obviously, our clock modulator. There's a bit of jiggery pokery going on here. I've got a bit of a problem with this. The capsule in the mic's no good. I mean, it's a 40-year-old radio. I'd say it's all its capacitors are shot as well, but yeah, so with key up, it's, you know, it's transmitting. I've got it set to 28 megs, and I'm just injecting some audio into it from the computer. I've just got one of these talking books going. Okay, and let's go and have a look at the radio receiving the signal. There's a bit of an issue. Okay, so we are receiving. I'm not, obviously we're going into a load, and we just obviously this receiver's close, so it's picking it up.
And a number of objects that again defied definition. At the far end of the room was what must have been the command and control.
I've just got an audio book going. Obviously, we're just ejecting it into the radio, but I can hear a 50 hertz hum there, which yeah, I think's the radio, because it didn't appear to be in the clock generator. It wouldn't be 50 hertz. Obviously, the mains electricity in this country is 50 hertz. I sort of know that sound anywhere, you know. So, but that's working. You know, we've got that noise. Yeah, well, it's that old radio. It's just probably wrapped with old caps, and yeah, it needs some TLC. I mean, the thing is over 40 years old, so yeah, it probably be a recapper's dream, I guess. But
my lord, brother, sister, Etri replied to me. What did you want? He seems ignorant of the best, she said. Etri actually scowled for a second.
Okay, so yeah, the test is a bit inconclusive. I've tested the output of the clock generator. That's clean. The noise is coming from how I am reacting with the old 11 meter radio. It is in pieces. I've got bits, you know, exposed. There's wires and jump leads running everywhere, and it's picking up noise. So, you know, I'm quite confident that this is okay. And you know, and I'm not going to go through that 11 meter radio, because that's not what this video is about. The video is actually about exploring this IC and whether it can modulate FM. And to be honest, it seems to be doing it quite well. It needs a bit of work. I think we need to look at this area. This is the voltage control. This is where the audio signal goes into the IC. So I think I need to sort of pay more attention to, obviously we've got this low pass filter, so I could probably make a sort of band pass filter and possibly an ALC circuit. So, you know, so it basically roofs, so it'll get to a level and not exceed, so that will stop any sort of distortion happening, which we noticed. You know, it was quite easy to overload the thing and start getting bent waveforms after a certain threshold. So I think an ALC circuit would probably go well. So, you know, I'm going to keep tinkering with it, and you know, as I make any major breakthrough, I will, you know, I'll make a video. But yeah, so I think a bit of filtering, and you know, it's about emphasis on certain frequencies, and I think I need to pay attention to that. So I need to go and do a bit more research. But that's basically it. It seems to be working. I'll leave a copy of the schematic if I can get it onto PDF. I'm sure I can. I'll leave that in the description. And if we look at the code, okay, so this is the code that we're using for this IC. Now, this code here actually covers, if you look, it's the VCXO. So if we can see if we can just zoom in a bit on that. Yeah, so this library here is different. It's got a B on it. I'll explain why in a second. But this is the code. It's pretty much as we went through in the last video, but as you know, because we want to use the VCXO segment of the IC, there's a few things we have to do. So, you know, well, first of all, we've got this initialization. I'm not quite sure what these two variables are doing here. They're both zeros, but I think this 8PF actually sets the it's the capacitance of the crystal. I'm not sure what the other options are, but I'm sure there will be if they're actually calling it 8PF. And here we can actually set oscillator, blah blah blah. Not really. These are just the comments that they put in there. So what we've got PLL B frequency. So whenever you're referencing that VCXO, you're actually referencing the PLL B, even though it doesn't appear to have one if you look at the block diagram. So what this, I'll put a figure in here. It comes set at 40, so I've put it at 1,000, and that's the pull, parts per million pull that you'll get. Now, exactly over what range, I'm not quite sure. So I've just literally just been playing with it, you know. So just by putting different figures, and I found 1,000 seems to work reasonably well. It could, I'm sure it could be improved. And we've got set arrow source clock 0 and, you know, PLLB. So I've got it set up exactly like this. This is, I'll show you where I got all this from, but I'll leave a link to a zip file, and you can sort of use this. So here we can actually tell it what frequency we want. Of course, we can just use a variable, use an integer. You know, it'll probably, you could get away with it. It's quite a long number. You probably get away with a long unsigned long int. That would probably do you there. PLLB frequency, because obviously we're telling it, we're giving it commands, because these are just talking to the library, and this is obviously a part of a function, and these are the elements within that function and what we're telling it to do. And as before, we've got the drive section, so you've got 2 milliamps. Now there's a bit down here with seal printing, and if you go through, there's a bit on GitHub. I'll show you in a second, but it will just basically, you can tell what the condition of the the PLLs, whether they're initialized and all that good stuff. So if you look, you probably notice that I've included SI5351B. Now there isn't a library called B. I've just called it that because if you use the library from the Arduino, and if you go into the manage libraries, if it comes up, you can actually search for libraries. The one you'll find in here isn't the right one, and that's what the problem is. It is it's just an old version, and these ones were actually last updated. The ones I've got were last updated in, I think, 2019. Yeah, okay. So you got Jason Mildrum and Dana H. Myers, which they've written this. There's loads of stuff on these. There's keep you busy if you want to play around with this stuff, because it certainly, I found it of interest. But what I've done, I've downloaded these. Well, I didn't download. I just copy and pasted them, and I've just renamed them to B. Because what happens is, if you use the normal SI5153.h, it will conflict with the one you've already got on the machine if you've already downloaded it. And I'll show you where I got it. It's just GitHub. Let's have a look. It's here. And again, I'll leave a link in the description. So yeah, you've got, this is the example. So if you go under SRC, you've got the header file and you've got the source file. So and all I do is just go in there and just cut and paste these, just create new files on your Arduino project. But I'll just leave a zip, and you've just literally open the zip and open the main file. So it just means that if you actually open this SI5351B _test001, and you open, obviously these two files will be in the zip file, so put them in the same folder, so it should automatically find them, and this will just run. And there's not a lot else you've got to do. You haven't got to set the I2C bus, because all these are the same. So not the bus, the address. I think it's OX40 when I tested it, but they're all the same, so you don't have to worry about any of that. You just literally plug it in and away you go. So there's quite a bit you can do there. And if we go back to the GitHub, there's loads on here. He's got examples. They've set up all sorts. Let's go back to that one. So there's calibrations. There's a hell of a lot here. There's all kinds. Got some algorithms to add. There's all kinds of sketches and all sorts here. Which I just don't have the time, but I will go and have a look. But they've been around a while, 5 years, 6 years, 7 years. So it's not anything new. But if you want to use the B, you need the later, sort of library file. Otherwise, it just doesn't work. So I think that's where a lot of people are going wrong. So okay, and if you want to have a look at the components that I've used, this is the one I've ordered, which is the 5153B-B-GM. Now you've got to be careful because some of these don't come pre-programmed. You have to flash them before they'll actually respond. I believe that's the case, and I know this one works. Obviously, you can see I've got it from DigiKey. So they're not that expensive. And the crystal that I use, where is it? It's here. So this one, so we've got a stability of 20 parts per million, frequency tolerance of 10 parts per million, 25 megs, and it's an 8 picofarad capacitance, low capacitance. And the thing is, the data sheet actually starts calling for, it wants this, so that's how I got it. This one works. It seemed to work for me, so I'm sure you can get one that's more stable. And the stability, there's a lot to it. It's temperature, and there's all sorts of stuff you've got to take into account, but this seems to work okay for me. So that's about it, really. I've done more programming with the Arduino. I've basically, someone asked me if I could do one of these things to control the 11-meter radios. I've done that. So this video I've sort of wanted to wanted to concentrate on being able to modulate FM on the thing. I think we've achieved that. So but if you want me to make more videos on the subjects, I'm happy to do so. I know programming isn't everybody's cup of tea. I just get mixed feelings about making a video and putting it on the channel that's dedicated to programming, because a lot of people may just it makes their ears fall off, and which is a shame, really, because it's quite fun once you get programming. I know I'm certainly no expert. Okay, all right. Well, look, if you watched the video so far, I'll just say thanks, and and just let me know in the comments what sort of content, and I'll see if I can get around to do it. And of course, I'll keep you updated as to any more developments with this and where I take it. But okay, thanks for watching. See you in the next video.